keyboard. Okay. So last time we just started doing the logarithmic differentiation, and that requires that we take a log of the entire problem prior to taking the derivative. And it's a really helpful tool because I'm sure looking at this problem here, you would never want to do that by doing the quotient rule. You'd also have a product and chains all in this problem. So this problem would be quite a task to do normally, but instead we can take log of both sides. I'm going to take log, I'll just call it f instead of f of x. And I'll take natural log of the other side. Now, the right-hand side, I can take and break that up into 3 logs. So the top functions, I can make natural log of 1 minus 8x plus natural log of 4x minus 7 squared. And then finally minus natural log of the cubed root of 5x plus 2. So then we've got this square up here that I can pull down, and I can rewrite the cubed root as a 1/3 power. So I can come down here, write the first one, bring that 2 down in front, and then bring the 1/3 down. Now I'm ready to take the derivative. So let's do d dx of this side. Same thing over here. Now the derivative of natural log is 1 over the inside times the derivative of the inside, which we'll just call f prime. Then on the right, somebody want to help me out with these? What would the first one give me? Not everybody at once. Not a clue.
Would it be like the 1 over 1 minus 8x?
So we'd have 1 minus 8x on the bottom, yeah.
And then the 1.
So there would be a 1, but we're going to multiply it by the derivative of the inside of the natural log. So what's the derivative of the inside there?
-8.
Yep. So that's what you got. Right, that 8 looks terrible. All right, what about the next one? Somebody else want to do that one? It's more of a request than a suggestion. So either you guys just tuned in and you're not really there, or you have no clue what we're doing. Either way, it's not good. So I'll do this one. Somebody else do the next one. I gotta pick somebody.
I got it. 5 over 5x plus 2.
Yeah, it's not that bad, right?
Yep.
Where
Right.
do we get the numerator from? Like, why are we just pulling those numbers?
We're taking, so derivative of a natural log is 1 over the inside of it. So for instance, the first one, we had 1 minus 8x inside, right? So we got that in the denominator. But
All right.
it's a chain rule because there's something other than x. So we also have to multiply by the derivative, which is minus 8x, or minus 8. So we do
Gotcha.
that for all of them. So we get a 4 and we get a 5. Okay. And then, of course, this number out in front just stays there, right? So they're there as well. All right. So a couple little things. We got to multiply the 2 and the 4 and the 5 and the 1/3 together. And then the last step is to take this f to the other side. So we have f prime equals f times. Give us a little more space here. This is minus 8 over this. Plus 8 over this. And you can write this a couple different ways. I think I'm going to do it like that. And the reason I left the space is because we don't want f at the end. We want to replace f, and f is equal to the original function. So that would be the derivative. Any questions about that guy?
Wait, I have a question.
Yep.
Why did you put the original function in front of all of that?
So when you take the derivative of natural log of f, remember that's when you do that implicitly, you get the derivative of natural log, which is 1 over f. But then you also get the derivative of the inside, which is f prime or df dx, whatever you want to call it. And the goal of the problem is to find f prime. So I just multiplied the other side of the equation by f and then plugged back in for f.
Okay.
If you go back and look at the other example we did the exact same thing.
Gotcha. Thank you.
All right, so here's an example. An automobile dealer, it's estimated that he can sell N cars annually. X is in thousands of dollars and is the amount spent on advertising. Find the number of cars sold if 6,000 is spent. So if X is in thousands of dollars, then X equals 6 here. And so we would just plug in. Just find my notes real quick. I think I have this written out. This one I have recalculated down. So let's see that sheet. me just calculate that real quick. So natural log of 4 times 72 plus 420. So that comes out as about 519.8. So this says number of cars. So we can't have 0.81 of a car. Let's say about 520. All right, find the rate of change in number of cars sold if 6,000 is spent. So rate of change, we need dn dx. So derivative of a constant is 0. And then we've got natural log there. So we get 1 over the inside times the derivative of the inside, which is 0.5. So we can get rid of that 0. And again, we just need to substitute in x equals 6. It looks like the rate of change would be 9 there. And last part, or this is another problem, sorry. It says daily demand for a product is given by this equation. Find the maximum daily revenue. So this guy is demand. Remember, revenue is x times that. So it is minus 8x natural log 0.01 times x. Then we want a maximum. Whenever you see that word, you should be thinking derivative. So I want dr dx. And if I want a maximum, that means I have to set it to 0. So now let's take the derivative. We would get minus 8 times the natural log. Because I would take derivative of x, that would give me 1. And then leave the x alone. Derivative of natural log is 1 over the inside times the derivative of the inside. Those would cancel. X's would cancel. So we have this. So we could divide through by -8. Have that. Just got to continue to solve for x. So get the natural log by itself. Raise both sides by e. Cancel. So whichever whichever one of those you like, 1 over e or e to the minus 1. And finally, x is equal to, I'm going to leave it as this. Comes out as 36.79 or approximately 37. Which thankfully fits within the domain. So it looks like the price would be, sorry, the number of units, x, would be 37. So we were asked to maximize the revenue. So we took the derivative, set it to 0, and solved.
I have a question.
Yeah, good.
When you subtracted 8 from all of those sides, why was it still 0 instead of like -8?
I did not subtract the -8. I divided.
You divided it? Okay.
Yeah, you could do it that way. You could come back here and say -8 log equals, and I would have to actually add 8 to all sides,
Yeah.
and then you would divide by -8. So then,
So it'll come out as the same thing anyway.
yeah, it should.
Okay. Thank you.
All right. So let me go ahead and share the other screen. So that we can do derivatives of exponentials. So e to the x is always my favorite, along with all of my students, because it's so easy to differentiate, right? E to the x has a derivative that is itself e to the x. The only change then is if we have something other than x up there. So here you see we've got e to the gx, which is some other function of x. And so when we differentiate that, we still get e to the gx back, but multiplied by g prime. So not a whole lot of extra stuff. So let's go ahead and demonstrate that. This first one's pretty straightforward, right? I'm asked to just find the derivatives of all these. So y prime, we still get our 3x squared like we would with our power rule. And then the derivative of e to the x we all love because it's e to the x. So then, part B, if I want to find y prime there, this is now a product. So I need 3x squared, leave e to the x alone, plus leave x cubed alone, derivative of e to the x. And you might want to write that as a factored form. So take out an x squared e to the x. Write it that way. I suggest that just because if you were asked for, say, a max or a min kind of thing, you'd want to factor it that way to solve. So those are very basic forms. Here's one where we've got e to some other power. So when I differentiate, I still get back e to that power. But I have to multiply by the derivative of that power. which in this case is 2x plus 3. So there's that guy. All right, so this example here is going to ask us to now expand upon that further and find intervals of concavity, or concavity, however you like to say it. So what derivative test do I need to find if it's concave up or concave down?
Second derivative test.
Right, that's second derivative test. So I got to find first derivative so that I can get to the second. If I take derivative of x, I get 1. And I leave e alone, then leave x alone, and the derivative of that exponential would be that. So I can rewrite it. Like so, and I eventually could factor this out. However, I don't want to do that yet because I have to take another derivative. For my second derivative, I'm going to be looking at this form. So derivative of e to the minus x is minus e to the minus x. Right, the derivative of the inside is -1. The next term, I'm going to take derivative of x. That's going to leave me with minus e to the minus x. And then I'm going to leave the x alone. Derivative of e is minus e to the minus x. So simplify that. That's going to be x e to the minus x, right? Because this and this make a plus. And then minus 2e to the minus x. Again, I'm going to factor that. I'm going to factor out the e to the minus x. And it looks like that. So I know that factoring is always something that people hate to do, but it's actually really important in this case. So the reason is, right, if I want to find the concave up and concave down portions, then I got to set this thing to 0 to find my inflection points. But there's no way for this guy to be 0. And if that's not apparent to you, right, this is e to the x, and e to the minus x looks like this. Right, there is no way for those functions to equal 0. So if that's the case, then only x minus 2 could be 0. Get x equals 2 for the inflection point. Do our number line. And then use test points. So if I plug 1 into this equation here, the e to the minus x is always positive, and then 1 minus 2 is negative. So I get a negative there. And if I plug 3 in there, get positive. So that means minus infinity to 2 is concave down, and then concave up from 2 to infinity. Any problems with that? Hey, running out of time. So it says we have 10 minutes left, so I'll see if I can finish up the majority of this packet. I think there's only one problem left. So let me finish this up, and then I'll send you another meeting so we can start 5.5 today. So demand for a product is given by this equation, where X is the number of units sold each week. Find the number of units sold that will yield maximum revenue. Well, revenue again is X times the demand function. So R is equal to X times D of X. And so that equals 140X e to the minus 0.05X. I need to differentiate that because, again, I'm asked for maximum. So that's dr dx equals 0. Derivative of this guy, I need to take derivative of x. That's 1. I leave everything else alone. Add to that. Leave the x alone. Derivative of the exponential. I bring down the number up top, the negative 0.05, and then I get back the exponential. Simplifying that equation, I can factor out the 140 e to the minus 0.05x. That leaves me with 1 minus 0.05 times x. And then setting this guy to 0. This out here then means nothing because I could divide through 1 by 140 and it would disappear. And I could take the exponential and it can never be 0. So I only really care about when this is 0. And that's pretty easy to solve. You move your 0.05 over there, make it plus, and then divide by 0.05. So x comes out to be 20. And again, an indicator that you did something wrong is if that number didn't fall in your domain up here. So if we want to maximize the revenue by selling products, we'd have to sell 20 units each week. And then what is the price per unit that will yield the maximum revenue? Well, we've already found where the maximum revenue occurs. So we just need to solve for that. So we would do 140 e to the minus 0.05 times 20. And I'll spare you the calculation. This is 51.5 approximately. So any questions about those problems, guys?
Nope.
Nope. All good.
So it says I've got about 5 minutes left. I think I'll just go ahead and end this meeting, and I will start another one. Like I said, I want to at least start 5-5 today, and then I'll have to. I think I can put that up on Blackboard quickly. So let me go ahead and